Today we are going to discuss on a topic which is very important, which is regarding unlocking the black box, basically solving the blast furnace to air failures. And these could be achieved by using advanced sensors and data science to predict and prevent industrial heart attacks like these, to air burnings. So unlocking those black box, we uh, feel like the blast furnace is just one giant, unpredictable, and it is difficult to predict anything. So we pour millions in, but sometimes it feel like we are just hoping it doesn't have an industrial heart attack. Here is the thing: we analyze over 500 process variables across three major industrial plants, TKSE, ISD, and VSL, to finally see inside that box. On the right, check out that glowing 3D wireframe. That blue ring represents 190 days of continuous and regular optical monitoring. And this gives us a confidence. It means we have moved from guessing to knowing exactly what is happening in the real time. But before we solve the mystery, we have to look at how much these heart attacks are actually costing us. And without that, none of is going to sensitize. As for the two-year failures are concerned, they are unpredictable, expensive, and disruptive. Is known to each one of us. When a two-year rupture, the whole furnace goes into a cardiac arrest sort of thing. So look at the image on the right, that red glowing fissures. It's a critical failure rupture. On the left, you see the annual impact bar chart. We are talking about 30 to 120 failures a year per furnace. So how much production is lost in those 2 to 8 hours downtime window? So these are not just parts failing, they are massive holes in your profit margin and your CO2 targets. So to plug these holes, we had to find a way to see what was previously invisible. So to fix the problem, we had to see the invisible. So question arises, how do we look into 1500 degrees centigrade anatomy interior without everything melting? So we launched a three-pronged intelligence approach. The first, we embedded thermal sensor at 5 mm and 10 mm depth inside the copper itself. Then we aimed SD cameras directly through the blast pipe with a 3.2-degree field of view. And this leads to uh, we can say that by combining the hardware vision and the data mining, we created a digital nervous system for the furnace. And once that system was live, it showed us that damage is not random, it has a favorite spot. And coming to our next slide, which is 85% of physical damage occurs at the extreme top and bottom, is been nicely visualized in the slide. So this is known from the data that top and bottoms are the main culprits. So here the things, your tuyeres do not melt evenly. Our sensor revealed that what we just rephrased, that 85% of damage is concentrated at the absolute top and bottom of the nozzle or the tuyer. So look at this radar chart. These bright neon coral spikes, those are sudden heat flashes jumping to 400 degrees centigrade in as little as 30 seconds. And so this leads to what? So if you are only looking at the average temperatures, you are missing the lightning strikes that are actually killing your hardware. One of the biggest reasons for these strikes uh, turned out to be a simple mechanical flaw in our cooling. Stagnant cooling water is also leads to violent thermal cracking that we have already discussed in our previous presentations also. But here also we try to include the stagnant water is a killer in high heat environment. In the blueprint on the left, look at that red circle labeled dead water zone directly below the outlet. The water stalls. Analogy wise, it's like a stagnant pool in a river. The heat just sits there. So look at the simulation on the right where the water stalls, the copper hits 400 degrees centigrade and crack. So what is the result? We found that zero heat removal in these zones is the primary cause of thermal cracking. While the sensor caught the heat, our cameras caught the metal actually being eaten, and which gives us a real result. Coming to the optical cameras part, which basically catches the erosion in the total operation of the furnaces. Did you know we recorded 190 days of physical destruction? This grainy image is an actual camera feed from the inside the furnace. Those neon outlines, those are detected bulges and the notches being tracked by an algorithm. So what is the result? Our algorithmic tracking confirmed a 100% match with the physical wear found after the 2 years were pulled. We can now see the erosion it happens, but seeing the damage is one thing, predicting it requires us to filter out the noise. So let us discuss on the principal component analysis. This is these distilled the 500 chaotic variables into three critical triggers, and which makes our analysis much easier. Now, how do we make the sense of 500 variables hitting you every second? We use PCA, that is principal component analysis, to act like a filter. We took that noise on the left and distilled it into three spheres at the bottom. Heat balance number 1, gas permeability number 2, and slag chemistry number 3. And this gives what? We realize that failure is not a freak accident. It's a direct result of these three things shifting out of balance. Think of it like a massive traffic jam happening inside your furnace. Now, coming to this traffic jam philosophy inside the furnace. Here is the thing, when slag basicity jumps, the liquid inside becomes a thick sludges. Follow these four blocks. The sludge pulls up, creating a deadman zone that blocks gas flow, and it's a highway detour. The gas is forced to detour the sideways, blasting directly into your two-year wall at over 3 megawatt per meter square, and which is a very impactful result. The jam in the middle of the furnace is what's actually melting your hardware on the edges. And we found the exact speed limit where this jam starts, as it is very clearly shown in the slide. So let us discuss the danger zone, the silicon distribution over 2.0%. So this is the most important number of the day. 2% looks at this scatter plot. The blue dots are normal, but once the silicon distribution crosses that orange line at 2%, the tapping rate suffocates. And these result the adverse effect of burning tuyeres, damaging tuyeres. So above 2% extreme hit load and hardware failure becomes a mathematical certainty. So we can actually see these fingerprints of the failure before they hit that 2% mark. So recognizing the fingerprints of the failure. So as it is enumerated in the table, by comparing safe periods against the failure period, we build this diagnostic matrix. When you see a 36% spike in silicon and a 16% drop in your tapping rate, you are officially in the irregular red zone. So what it gives us the feedback, these tables gives operators a clear early warning that the furnace is drifting into the danger zone. However, sometimes the way we try to fix a cold furnace actually causes the storm. Now coming to the extra coke paradox, and we know the experience of this extra coke is not good. So have you ever tried to fix a problem and only made it worse? So when operators see a disturbance, they often add extra coke to keep it hot. But look at the overheating storm map on the right. The extra fuel chokes permeability, causing pressure and heat to spike violently against the specific tuer. And this result a massive. So the fix backfire and create the very hardware rupture we were trying to avoid. So if we cannot always fix it with the fuel, we had to fix it with the better engineering. So now coming to this slide, and this is all about what we talked just now. This is about the designing the unbreakable heart. So we decided to kill the dead water problem forever. We moved from straight channel to this, a spiral cooling architecture. The water is forced to spiral around tip in a continuous flow, and which result a magic. We permanently eradicated the stagnant zone. The copper stays chilled regardless of what chemical storms are happening in the furnace. This engineering combined with our data leads to the ultimate goal of which is totally depend on the prediction. So from reactive repair to predictive prevention. So what if I gave you a 20-minute head start? Look at this real time monitor. The blue line is stable, but as it approaches the red failure threshold, the system trigger a warning. And what it gives, because we can predict a failure 20 minutes before it happens, operators have a window to adjust the blast and save the equipment. So we have moved from flying blind to having a totally transparent furnace. So now coming to a transparent, intelligent and resilient furnace, we have illuminated the black box by combining 190 days of visibility, the intelligence of the 2% silicon threshold, and the resilience of a spiral cooling. We have changed the game, and which resulted a magic. We are talking about a massive saving downtime cost and emission. The furnace is no longer a mystery, it's a managed